Hello everyone again. I'm Roberto Foddis, Senior Business Development Manager in Active Technologies, and I'll present today with my colleague Stefano Parma, Principal Technical Sales Engineer. The topic of this talk is high performance AWGs and their use in nowadays research and development application. Let's have a look at the agenda of this meeting. We'll present you briefly Active Technology Company, our product catalog, and the key features of our new products that we design and produce here. Then Stefano will talk about the modern arbitrary waveform generators and their main applications, followed by an impressive live demonstration. Don't miss it. At the end of the webinar, we'll be happy to answer all your questions. Just some info about the webinar. It is now being recorded, and in a few days, we'll send you the link of the video registration. This link can be shared to anyone, as it doesn't contain any confidential information. Please use the GoToWebinar chat box to communicate with us for any technical issue, and the question box for all your questions. We'll try to answer all your questions at the end of the webinar. If we are not able to answer all your questions, we'll write you back at your registration email. We expect to have a length of this webinar about 1 hour and a half. Okay, just a few words about the company. Active Technologies was founded in 2003 when two electrical engineers of the local university decided to bring to the market the technology they had developed during their PhD. For anyone who doesn't know University of Ferrara, it was established in 1391 by Pope Bonifacio IX, and Niccolò Copernico took his degree here in 6th century. Ferrara is a medieval town located in northeast of Italy. Interesting to know, the first business of Active Technologies was not to produce benchtop instrumentation as today, but to create automated test equipment for testing flash memories. In 2007, the company became fully private and established a new headquarters in Ferrara in the same location we are today, but now we have much more space for offices and labs. When flash memories business started to decrease, Active Technologies began to collaborate with famous test and measurement multinational companies, shown in the slide, Tektronix, National Instruments, Teledyne LeCroy, to develop customized AWGs in USB and PXI formats. Those products were produced in Ferrara, but rebranded and sold directly by those companies. Currently, we have a pair of active OEM contracts with a dual brand design. So you can read powered by Active Technologies on the front panel of the instrument. Teledyne LeCroy AWGs are mid-range products with customized specs, and they are sold worldwide by LeCroy sales organization. Berkeley Nucleonics rebranded all our instruments with a different front panel color, but in this case, they are allowed to sell only in US market. In the last 4 or 5 years, the company management decided to focus all R&D efforts to develop new products being sold only with Active Technology brand, not accepting further OEM contracts. This because we are now a mature company with a well-established distributor network in the world. The signal generators category include arbitrary waveform generators, if you want to generate waveforms of any shape, arbitrary function generators, to generate standard periodic waveform, and pulse generators to manage only square pulses, but with many different parameters. During the last years, we added specific features in our AWG models that are not offered by any of our competitors. First of all, AWG-5000, that Stefano will present you after my talk, is the fastest 16-bit AWG available in the market. Second, we offer as an option the possibility to add multiple digital LVDS or LVTTL output channels on the back of many instruments. Remember that both analog and digital channels are fully synchronized. Third, our AWGs have the largest amplitude range available in the market for a specific sample rate, up to 24-volt peak-to-peak for AWG 4000. Last but not least, if you need a multiple channel AWG, we can offer a single instrument with 8 independent channels in both 4000 and 5000 families. Which are our customers? In the industrial area, we work very closely with semiconductor and aerospace and defense R&D department, where complex analog signals need to be generated. In the research community, we sell our product in many different fields, from big physics organization like CERN to quantum computing labs. Last year, by the way, we held a dedicated webinar on this topic. You can watch it in YouTube if you want. We can send you the link. Telecom and automotive are also important markets. For example, to solve applications like the sensitivity testing. We are also running several European projects as an industrial partner. This is very important for us to stay in touch with the most important universities and research organizations in the world. Let's start a brief introduction to the new product portfolio of Active Technologies. A T-Rider series is the newest family of arbitrary waveform generators and pulse generators we offer today. All these instruments are 3U8 and sold as bench-top units, but can be easily mounted in a 19-inch rack. You can benefit of a 7-inch capacitive touchscreen on the front panel, as well as several knobs and buttons to work in a classical way. A remote connection to the PC is possible with Ethernet, USB, or GPIB optional port. Here we have a snapshot of the specification of our 3 AWG subfamilies in the Rider series. 2000 is the cost-effective family with up to 4 channels and a sampling rate of 600 megasamples per second in real time. 4000 models are the medium performance unit with up to 8 channels at 1.2 gigasamples per second and a signal bandwidth of 318 MHz. This product offers also a high amplitude range with a programmable hardware offset. 5000 is the top model and is the focus of this webinar. You have up to 8 channels, resolution 16-bit, over 6.16 gigasamples per second on sampling rate, and 2 gigahertz of instantaneous bandwidth. Thanks to the RF mode option, you can double the sampling rate to 12.32 gigasamples in IQ modulation. Another important member of the Rider series is the PG-1000 high-performance pulse generator. This generator is able to generate multiple pulses or pulse train with an impressive rise-fall time of 70 picoseconds and a minimum pulse width of 300 picoseconds. The amplitude is selectable with an adjustable offset of 2.5 volts. This product fits very well with semiconductor and big physics application where you need to emulate the digital signals. Here you find just a comparison of two oscilloscope snapshots where we generate pulses. In the first case, very narrow, 300 picosecond with PG-1000 pulse generator. And this, in the second snapshot, you see a high voltage pulse, 24 volt, generated by AWG 4018. So in this case, we have an AWG used to generate pulses. Okay, my talk is finished. I give the ball to Stefano that will present you the technical part.
Okay, thank you, Roberto. Hello, everybody. I'm Stefano Parma. I will guide you into the technical part of this webinar and also into the live demo. I have now a few slides to introduce the technical points. Okay. So now let's try to figure out why you need a signal generator. In most cases, when you need to test an electronic device, you have to apply a direct stimuli to the device and the test. So typically, the DDS arbitrary function generator produces the most common test signals that are used in laboratories and design departments all around the world. The reason is that AWG deliver an excellent frequency agility, and they have also modulation features. But function generators cannot match the arbitrary waveform generator ability to create any kind of waveform with high precision and accuracy. So basically, these are the main reasons why you need an AWG. So they are used for device characterization, compliant test measurements, and they are used also to create pure signals, but also to replicate real-world signals and very complex scenarios. Here in this slide, we see on the right, three pictures of signal sources, because typical signal sources are arbitrary function generator, arbitrary waveform generator, pulse pattern generator, RF generators, and AC/DC power supplies generators. In this webinar, we will focus our attention to arbitrary function generator, arbitrary waveform generator, pulse, and pattern generators. The technologies behind the signal generator instrument are essentially two. The first one is DDS techniques, and the second is the AWG technique. You can see here a block scheme of a direct digital synthesis technique that represents the core of arbitrary function generator instrument. Here, we will not describe this technique because we will focus on AWG technique, that is the core of arbitrary waveform generator instrument. Then there is another category of signal generators that are digital sources, and our instruments are able to not only generate analog channels, but also digital channels that are perfectly synchronous with the analog ones, and we call it mixed mode. A quick history about arbitrary waveform generator. The first AWG appeared in the market during the 80s, and the most of the features of high-performance arbitrary waveform generator were introduced by Hewlett-Packard. Here we see a model that is HP 8770A, and it is a waveform generator with 125 megasample per second of real-time sampling rate, with 50 megahertz of analog bandwidth, 12 bit of vertical resolution. This instrument has also memory segmentation and also sequency features that are available also today to the modern arbitrary waveform generator. So during the last years, AWG have become the reference instrumentation category for applications that requires the generation of real-life signals. So in general, you can address a very wide range of applications using this kind of instrument. For example, nowadays they are used for quantum computing experiment, for RF or wireless for communication, but also for defense electronics, big physics or advanced research in electronics and chemistry, radar and LiDAR testing, aerospace and defense, semiconductor test, automotive, but in general, when you need to simulate real-world signals. So since there are many applications, this application requires usually different form factors. Here on the right, you can see arbitrary waveform generator with different form factors. For example, here we can see a USB instrument, then a PCI or PXI module, and the benchtop instrument. Benchtop instrument will be the focus of this webinar. There is another category of instruments that are rack-mounted. They are instruments that allows you to insert your arbitrary waveform generator into a rack with other instrument, and you can control this instrument by remote. I would like to highlight that also our instrument can be inserted rack because we provide a kit for rack mount. Well, we arrived to the AWG block scheme, and usually the core and all the control part of an arbitrary waveform generator is developed using a FPGA, and this FPGA control a waveform memory that stores the samples of your waveform, and it also a digital to analog converter. And there is also a clock circuitry that synthesizes the clock that is needed to clock the FPGA, but also the memory and the digital to analog converter. So the samples are read from the memory, and after that the samples reach a shift register that makes a parallel to serial converter of the digital data that are sent to the analog converter. This component converts the digital data into analog signals. So at the output of the digital to analog converter, you have an analog signal that is very small in amplitude. So in AWG circuit, there is a output stage that is analog output circuit amplifier stage that allows you to amplify your signals. So at the end, you can have a higher voltage waveform for your test. It is important to understand what are the main parameters and characteristics that are important for arbitrary waveform generator, because it is useful for a customer to understand what are the topics that they have to focus before buying an instrument. The first parameter that usually you have to take care about it is the sampling rate. That is the maximum clock frequency used to read the samples from the memory. There is a Nyquist theorem that puts in relation the sampling rate with the maximum frequency, and the sampling rate must be 2 times the frequency the maximum frequency. In our model AWG-5000, we have 2 modes. In baseband mode, we have a maximum sample rate of 6.16 sample per second. In RF mode, we have a 12.32 gigasample per second. Now, okay, we will see later the sampling rate and an example of how to change the sampling rate in our instrument. Another important parameter is the memory depth or record length that tells you what are the maximum number of points, samples that can be stored in the waveform memory. For example, our AWG-5000 has up to 4 gigapoints per channel with a wafer granularity of 1. A third parameter that we can analyze is the timing or horizontal resolution, and it is the inverse of the sampling rate, and it represents the smallest increment that can be used to create the waveforms. Speaking about vertical resolution, it is the bit of the digital to analog converter. In our instrument, we use 16 bits of vertical resolution. It is important parameter because an higher bit rate means that your waveforms, your signals can be reproduced with more details. It tells you also the minimum output signals that level that the arbitrary waveform generator can generate. Speaking about the analog bandwidth, usually it is the -3 dB bandwidth, the signals coming out to the arbitrary waveform generator. So this parameter, analog bandwidth, the sampling rate, but also the output circuit states, gives you a focus on the maximum frequency of the signal that you can generate. About the output circuit stage, it contains usually the amplifier, and so it tells you what it is the maximum output voltage and also DC offset that the arbitrary waveform generator can generate. For example, in our instrument for the 5000 model, we can reach 5-volt peak to peak into 50 ohm. About 2000 model and 4000 model, we can reach 12-volt peak to peak. And they are combined also with an hardware offset. So you can shift in hardware up and down your signal for a total of 48 volt on high impedance of voltage window. Some instrument, for example, our AWG-2000 has also a 10 times attenuator, and it is useful because it allows you to create a very low level signals generator, very low signals with a good ratio between signal and noise. Well, other parameters that are important are the number of channels, because nowadays application requires many channels, like for example, automotive, but also quantum computing application. So more channel you have, it is important for your application. Then some arbitrary waveform generator, like for example our instrument, they have also digital channels, not only analog channel but also digital. And in our instrument we can also link together multiple instruments to increase the number of the channels. Another point is the sequencer, that it allows you to create a sequence of waveform. And for example, in our instrument, we can create a sequencer with up to 16,000 entries. Here we can see a picture of a multi-channel system. We have linked 4 instruments. Each instrument has 8 analog channels. So this system allows you to generate up to 32 analog channels and 128 digital channels perfectly synchronized with the analog ones. For example, if you need to test a quantum system with a system like that, you can test up to 32 qubits using RF mode with a skew resolution of 100 femtosecond. So we arrive to the presentation of AWG-5000 that will be used for the live demo. At now, the 5000, it is the world's fastest 16-bit arbitrary waveform generator. The main feature of the instrument are the following one. You can find the instrument in 2, 4, or 8 analog channel configuration. Maximum sample rate is 6.16 gigasample per second with 16 bit of vertical resolution. The instrument has 2 GHz of analog bandwidth, and you can create up to 5-volt peak-to-peak with hardware offset. It means that you can create a signal from 0 to 5 or from 0 to -5, so a 10-volt peak-to-peak into 50 ohm of voltage window. The instrument has up to 4 gigapoints of waveform memory per channel. You can create also digital channel, not only analog channel, so up to 32 digital channel. And there are 3 different user interface. One user interface for arbitrary waveform generator mode, another one for arbitrary function generator mode, and the last one for serial pattern generator mode. And you can also synchronize multiple instruments together. Here just a screenshot of a sine waveform of 5-volt peak-to-peak at 1 giga that we will see live in a few minutes. And here a pulse of 5-volt peak-to-peak with 110 picosecond of rise and fall time. So I would like to highlight that we can reach 5-volt peak-to-peak with 110 picosecond of rise and fall. So we arrive to the description of the front panel. For this description, I will switch to this to the real instrument. And now 1 minute that I will show you some feature of the instrument live. So the instrument is equipped with a 7-inch touchscreen display here. So here you can use the touchscreen, and you can command your instrument like a tablet. So it is very easy to use. And this is the 7-inch touchscreen display. If you want, you can also command the instrument using a soft keyboard, so knobs and buttons like all the standard instrument. So here we have the soft keyboard, and here it is the 2-channel model. We have 2 analog output, 2 SMA outputs, that is this one and this one marker output, and on the front we have 2 trigger inputs, trigger input 1 and trigger input 2. Here we are seeing the rear of the instrument with other connectors that are reference clock in, reference clock out, and external clock out. And here we have the digital connector that allows you to connect a digital probe, LVDS or VTTL probe. It allows you to generate digital signals. And here we have standard computer ports like LAN, like USB, and so on. Okay. Okay, we continue with the presentation, and we arrive to the live demo. About the setup of this live demo, you can see here that we have connected the AWG 5000 two-channel version to an oscilloscope, and both they are controlled by remote. The first demo will be about arbitrary function generator mode. In this mode, the sampling rate is fixed because the instrument is like a benchtop function generator, so you can create a basic waveform like sine, cosine, pulse, and so on. And for example, you can create a 2 giga sine waveform, 5-volt peak-to-peak square waveform at 770 megahertz, or 5-volt peak-to-peak sine wave at 1 giga, or 4-volt peak-to-peak at 2 giga. And the jitter is very low, it is below 2 picosecond. So for this first demo, we will take a look to to double pulse mode. That is a mode that we have developed for semiconductor testing, for the test of IGBT or MOSFET testing. Okay, so now we will switch to the user interface of the instrument. Here you can see the user interface of the instrument in AFG mode. And here you can see the user interface of the oscilloscope. So everything that I will do now with the mouse, you can do it with your finger, because we have just seen that the instrument can be controlled with the touch screen. A quick description about the user interface. Here in the bottom you have the command bar that contains several buttons to control the instrument, like start and stop the instrument, send the software trigger, turn on and turn off the analog channel, access to the settings, access to the waveform, and after that we have another button that you can control the instrument by remote, and so on. Here in the upper part we have the waveform parameters in terms of amplitude, offset, frequency, and phase. And these parameters, they will change accordingly to the waveform that you have selected here. Here we have a graphical representation of the waveforms that you will generate. With these two buttons, the first one, you can select what is the basic waveform that you want to generate. With this one, you can select the mode. There are mode, continuous modulation, because you can make AM, FM, PM, FSK or PSK modulation, also PWM. You can make a frequency sweep, or you can make a burst of waveform. Let's start with the double pulse mode tab. We select double pulse, and as you can see on the user interface, there are two pulses that you can change the parameter of pulse 1 and pulse 2 using these two tabs. So we can create one pulse positive, and one negative, or two positive. Let's make the first one to positive. Then let's change the pulse width, 40 nanoseconds. Now let's go to the second pulse. I change the amplitude to -1 volt, and I change the pulse width to 50 nanoseconds. Now I press the run button, and the instrument will start generating. One moment that I need to set the oscilloscope, and now I will show you the generation. So as you can see here in the oscilloscope, we have pulse 1 and pulse 2. So the instrument is generating pulse 1 and pulse 2. Now you can change, using this mode, all the parameters runtime without glitches. So for example, we can go to the pulse 2 delay, and we can change the delay of the pulse 2. Now I'm going to change the delay, and as you can see, I'm changing the delay of the pulse. In the same way, we can change also the width, for example, of pulse 1. Now I'm going to change the width of the pulse 1. And I can also change, for example, the rise and fall time. Now I'm going to change the rise time. So here I'm changing the rise time. And I can also change the fall time. So in this way, I'm changing the fall time. So all the parameters can be changed very easily and without glitches. And the instrument has also a built-in noise generator, Gaussian random noise generator, and you can apply also the noise runtime. For example, now I will try to add some noise. As you can see, our waveform is noisier. Okay, now for the second demonstration, we will switch to the other application that is through ARB, that is Arbitrary Waveform Generator mode. So now the instrument will switch to Arbitrary Waveform Generator mode, and in the meanwhile, I will describe you the second example. So Arbitrary Waveform Generator mode, in this case, the sampling rate is variable, so you can change the timing of your waveform, of your instrument, and you can set it as you want. We have up to 4 gigapoints of waveform memory per channel, and the rise time is 110 picosecond. You can generate also digital channel, as you can see here, that are synchronous with the analog ones. And we already seen that on the front we have 2 independent trigger input signals. So the first demo with Arbitrary Waveform Generator mode will be about optical modulators. So an optical modulator is a device which is used to modulate a beam of light. So it is fundamental controlling optical modulator sending laser pulses on a system. So Arbitrary Waveform Generator like AWG-5000, they combine very high amplitude with very narrow pulses, and these kind of pulses are very important for this kind of application. We can create 3 volt, but also 5 volt peak-to-peak rectangular signals to control these devices. In this example, we will see how to generate high voltage pulses for optical modulators or for laser drivers. So we go back to the application. You can see here that we changed the application, and this is the user interface of Arbitrary Waveform Generator mode. It is very similar to the previous one. Here below we have the command bar, but the core of the user interface is the sequencer that is here on the top. The sequencer contains several entries, entry 1, 2, 3. You can add up to 16,000 entries, and each entry contains the waveform that you want to generate. You can select your waveform pressing this button here. Each entry has several parameters in terms of amplitude, voltage high, voltage low, repetition, so how many times it will be repeated your waveform, and duration in terms of samples or time. So let's make our first example. We select as first entry, first waveform, a Gaussian pulse, and we set the amplitude of 5 volt peak to peak. So in this way we change the amplitude. Now I had a DC level that acts as a pause, and I make, for example, 5 repetitions of this DC level. Then I want to add a narrow pulse. We can create it since if we open here the waveform list, we can see that we have several waveforms that are in red, that are the predefined waveforms, as they are created by factory. But we can also create our own waveforms because we have another software that is called Waveform Editor. This software is part of the standard software package, and it allows you to create any kind of waveform. As you can see here, we have 2 analog waveform and 8 digital lines, so we can modify not only analog waveform but also digital. You can create a very complex waveform. Now we'll see an easy example. I select just the waveform 1, and then you can decide what is the waveform that you want to generate, sine, cosine, triangle, and so on. We set pulse. We set the amplitude, the offset, and we can set a very narrow pulse. Okay. We press the OK button, and as you can see now we have our new waveform. We can save it here on our list, save waveform list, and our pulse now it will be available in our sequencer. So we can go here, and we can select here in the list the narrow pulse, that I just created. I change the amplitude to 5 optic to peak. Now I add another DC level with an offset of 2.5 minus 2.5 volt. And now I want to add another pulse. This time I want to add an exponential one. So if I go here in the waveform and I go in the waveform editor, we can open the waveform editor here, and we can create also an exponential pulse. For example, we can set here 2 volt, and we can set 0 here. And so we create an exponential pulse. Now we can save it, and we can go back to the main application, where we can insert our exponential pulse. So here in the list, there is pulse exponential. I change the amplitude, and I add last DC level to 2.5 minus volt. Now we are almost ready. We have to change the baseline offset because this instrument is equipped with an hardware offset, so you can change it in hardware. And so we move the baseline offset to 2.5 volt. In this way, we will create pulses from 0 to 5 volt. So all these pulses will be from 0 to 5. On the second channel, there is a DC level. Now we are ready to generate our pulses. I press the run button, and one moment that I set the oscilloscope. Okay, so here in the oscilloscope we are seeing the 3 different pulses. Now I make a zoom and I make single acquisition so we can see it one by one. So this is the Gaussian pulse that we have generated of 5 volt peak to peak Gaussian. Then, okay, one moment. Okay, here it is exponential pulse, and here we have the rectangular one. So we have all the 3 different pulses. One moment. Okay. So rectangular, exponential, and narrow pulse. Now I would like also to show you how you can create a 5 volt peak to peak pulse rectangular waveform at the maximum amplitude and with the maximum minimum rise time of 110 picosecond. So just for simplicity, I set a square waveform, and I set 2.5 volt and minus 2.5 volts, so it is peak to peak, and I press the run button, and the instrument will start generating. Okay, so here on the oscilloscope, we are seeing that we have a 5 volt peak to peak from minus 2.5 to 2.5 volt. Here it is our pulse that has a rise time of 110 picosecond. So we have a pulse at maximum amplitude with a minimum rise time of 110 picosecond, 5 volt peak to peak. Now we move on to the next demo, And I go back to the presentation. Before the next demo, I would like to tell you that our instrument can be configured as arbitrary function generator, arbitrary waveform generator, digital pattern generator, and serial pattern generator. During this webinar, we will focus on arbitrary function generator and arbitrary waveform generator. But here you can see a screenshot of pulse pattern generator. So it is like a 4-in-1 instrument. You can control it also your instrument by remote because we provide a full set of SCPI commands, and we provide lab drivers, Python example in C++ or in MATLAB, and you can control the instrument using LAN interface, GPIB, or USB TMC. The serial data pattern generator option, it is an option, and it allows you to create pulse pattern with up to 1.54 gigabit per second. So in the next example, we will use the RF mode. RF mode is an option that allows you to run the instrument at 12.32 gigasample per second. It is a very useful option for quantum computing, but not only, also for wireless communication RF signals. So it allows you in general to create RF signals up to 6 gigahertz. So we will see that each entry you can insert up to 4 waveforms that in this scheme are I0, Q0, I1, and Q1. And this waveform will be divided by sine of F0, cosine of F0, sine of F1, and cosine of F1. Internally, they are summed, and at the output of the UFB, you will have a RF output signals made of 2 carriers, one of 3 giga and the other one at 6 giga. So you can have RF modulated signals with 1 carrier or 2 carrier. It is very useful, this mode, because in this way, for example, if you are using the instrument for quantum computing, you can double the number of the qubits tested with a single instrument, because you don't need anymore an external up converter. Well, in the next example, we will generate some sequences. They are very popular in quantum computing application. One, it is called dynamic decoupling sequence, and the other is a Karp-Parser-Mabon-Gill sequence. So this is a dynamic decoupling, and this is the Karp-Parser-Mabon-Gill sequence. Now we'll start with the demo. We'll see how to create this waveform. We will switch now in RF mode. So here in the device settings, you can change the operating mode from baseband to RF single carrier or RF double carrier. Let's select RF single carrier mode. And now you can see that we have I0 Q0 for channel 1 and I0 Q0 for channel 2. So we have to populate I0 and Q0. We go into the waveform list, and this time we will import the samples, because you can create your waveform using the waveform editor, but you can create your waveform also using MATLAB, LabVIEW, Python, and then you can export your point in TXT format or binary format, or also you can also export your oscilloscope file, and then this file can be imported in the instrument. So here we have already imported a dynamic decoupling sequence, and here we have a Karp-Parser-Mabon-Gill sequence. Now we will add it to the sequence, to the entry 1. Here we will load DD4 phase 1, and here also DD4, the same signal on I0 and Q0. For the channel 2, we will load the Karp-Parser-Mabon-Gill sequence. Okay, so we have loaded channel 1 and channel 2. If we go back to the settings, we can also change the amplitude, for example, 1 volt and minus 1 volt to make larger signals on I0, and also 1 volt and minus 1 volt on Q0. Then we can go to the channel settings. We can set the carrier frequency. In this case, we are in single carrier mode, so we can set, for example, the first carrier at 4 giga for channel 1, and also the second carrier at 4 giga for channel 2. Now we are ready to start the generation, and I press the run button. Okay, one moment that I set the oscilloscope. So as you can see here, we are generating this sequence. I zoom a little, and they are modulated pulses. As you can see, the frequency is 4 gigahertz, and so we are generating these modulated pulses that are useful for quantum computing test. It is important to understand that we can also change some parameter runtimes to create, for example, impairments. We can, for example, change the skew of I0 and Q0 runtime, but also the amplitude. And now we try to change the skew, for example, to 1 nanosecond. And let's see what it happens. Now, as you can see, I changed the skew to 1 nanosecond, and we get some impairments in the waveform. Now I set to 4 nanosecond, and we created another kind of impairments, since I0 is no more synchronized with Q0. And I can change also the amplitude of I0. Now I'm changing the amplitude of I0, and as you can see, the amplitude is decreasing. So we added impairments in real time without needing to load other waveform into the sequencer. Okay, we finished this demo. We can go on with the next one. So next demo, it is about the generation of RF wireless signals. We create IQ signals. In particular, we will import a multi-carrier signal made of 6 baseband carriers of 100 megahertz, 150, 200, 250, 300 megahertz, and 350 megahertz. These baseband carrier, they have an offset of 50 megahertz, and they have a modulation scheme of 16 QIM with a symbol rate of 10 megahertz. And I use a filter raised cosine. So let's see how to put it. So we go back, and also for this application, we will use RF mode. So we change to RF single carrier mode. And now I have already created our waveform, and I will import it. So here on the desktop, I have some waveforms, and I have a I waveform and the Q waveform that I've already imported. So here you can see multi-carrier I and multi-carrier Q. And now I go back to the main panel, and I insert in I0 multi-carrier I, and I will insert in Q0 multi-carrier Q. So I load the first entry of the sequencer in RF mode with the multi-carrier I and multi-carrier Q. Now, like the previous example, I will change the carrier frequency to 4 GHz, like before, and I will start the generation. So one moment that I set the oscilloscope. So here you can see the RF modulated signal. It is not very effective seeing to see that in the oscilloscope. But I took a screenshot of the spectrum analyzer that we can see here in the slides. So here you can see a screenshot of the spectrum analyzer, and as you can see, we have the single baseband carriers that have been up-converted at with a frequency around 4 GHz. Now we arrived to the last example of today's webinar, and this example will be about chirp signals generation. So usually chirp signals are signals that are modulated in frequency but also in amplitude, and they are useful for radar. Now we will go back to the application, and we set it to default because this time we will use baseband mode. We have to create this signal, and to do that we'll use the waveform editor. So now I will open the waveform editor. Here it is the waveform editor, and I set the number of samples to 10 kilosamples. I set the DC level to make the things more clear. And as you can see, your waveform is made of one segment, but you can add more components to your segment. For example, we can add another components because the components can be multiplied or subtracted together. So to generate a chirp signals, we need to import a trapezoid waveform that we can find it here. So here I have a trapezoid waveform. I will cut the header, one with 2 lines, and I press OK, and now our trapezoid waveform. That is component 1. For the component 2, we can use a formula. So I already prepared the formula here that we can copy. And we can paste it in the waveform editor because there is a possibility to make a formula. So I paste the formula and make a preview. This is a sine waveform that is frequency modulated. Now the two waveforms are summed together, but we need to multiply it. So we can go to the component 1 and we can set multiply. So this is our chirp signal that can be used for radar feature. We go back to the ARB application, and we can insert it in the sequencer. Chirp signal here, and we can insert DC level with 10 repetition, for example, and I press the run button. As you can see here in the oscilloscope, we are generating our chirp signal. That is this one, and I can make a zoom. As you can see, our waveform is modulated in frequency, but also in amplitude. So we arrived to the end of this demonstration, and now I let the speech again to Roberto, that I pass the screen to Roberto.
Just a moment.
1 moment.
Okay.
Okay, 1 moment.
Okay, thanks, Stefano, for your kind presentation. I think we are on time, 1 hour left, so we saved some time. It's good, I believe, because all of us, we have to work. But we have some time to answer your questions. So if you have not done yet, you can write, if you have any question, to the question box. We have a pair of questions ready. So I ask Stefano to answer. The first question is it possible to have a dynamic jump in the sequencer using a combination of bits?
Okay, thank you, Roberto. Yes, it is possible because the instrument has a dynamic jump feature that allows you to set in the sequencer dynamic jumps to change the execution of the sequencer dynamically. So in the rear, we have a 8 digital pin connector, and you can connect up to 8 digital lines. And so the instrument samples these lines, and you can set the jump in relation to the value that the instrument will sample. So yes, it is possible, and it is an option that can be also booked after by the customer.
Okay, thanks, Stefano. Second question is, what is the maximum rest time at 5 volt peak-to-peak in your AWGs, and which is the best model for doing that?
So in general, with the AWG-5000, we can reach 5 volt peak-to-peak, so a full bandwidth, so it's a maximum amplitude signals with 110 picosecond rest time. So we reach full bandwidth at 5 volt peak-to-peak, and this is the fastest rise time that we have in arbitrary waveform generator. If we talk about pulse generators, we can reach 70 picosecond with the PG-1000 model at 5 volt peak-to-peak, but PG-1000 generate only pulses.
Okay, another question just arrived. Just a moment. By using 2 different channels on the same instrument, can I generate 2 different signals having different frequencies F1 and F2? If yes, how high can be the ratio F1 F2?
If you use arbitrary function generator mode, you can do any kind of relationship from channel 1 and channel 2. So you can create a frequency on channel 1 and another frequency on channel 2, because since AFG mode use DDS technique, they are completely independent, speaking about the frequency. If you use arbitrary waveform generator mode, yes, you can have different frequency on different channels, but it depends on the number of points that you select on your waveform, because the sampling rate is common to channel 1 and channel 2. So if on channel 1 you insert, for example, a sign with 1000 sample, and on channel 2 you insert another sign with the 2000 sample, the frequency on channel 2 will be 2 times than the frequency of channel 1. So it depends on the number of points and on the sampling rate.
Okay, thanks, Stefano. There is another question, very with a lot of yes, not easy to answer live, but maybe can you say some words about cycling, how to reload this in a continuous way waveform in the sequencer? So how to do cycling?
Yes, it is possible because we have different run modes. If it is possible, maybe I can share my
Sorry.
screen.
Just a moment. Okay, Stefano. Okay, go on.
Okay, thank you. So if we go here to the settings, there is in device settings the run mode. So the instrument can work in continuous, so all the waveform in the sequence are repeated continuously. Then you can switch to single burst. It means that all the waveform will be repeated for a number of times that you write here. Triggered continuous means that the instrument waits for a trigger here before starting the generation. Stepped means that the instrument waits for a trigger here before generating this waveform, then waits for another trigger here and generate this one, and so on. But we have also an advanced mode that allows you to create very complex waveform scenarios. Now, I will not go into the details, but we have wait event extraction, jump if event extraction, jump, and go to entries. So in general, you can do what you want with your waveforms. One moment that now I will give again the control to you.
Okay, I think we can close the meeting, the webinar. So thanks a lot for your participation. I hope it was interesting. I believe so. So please write to me and Stefano if you have any question and the information if you want a dedicated demo in the future. So we are here to help you working with the generation of signals in your experiments. So thanks a lot. Have a good day and see you later. Bye-bye.
Bye-bye. Bye-bye.